Hello and welcome back to Unbounded Operators, the video series where we extend our functional analysis knowledge to non-continuous operators. And indeed, in today's part 12, we will continue our discussion about the Hilbert space adjoint. In particular, we will look at the connection between the kernel and the range. However, as always, before we go into the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And you might already know, as a Steady supporter, you can download additional material with the link in the description. And then without further ado, let's immediately start with the general assumption of today, where x and y are Hilbert spaces. This is important because for a given operator t between x and y, we want to consider the Hilbert space adjoint t star. Hence also here, it's a general assumption that t is a linear operator and it can be bounded or unbounded. However, of course, the bounded case is much simpler, so you should usually think of an unbounded operator here. And in that case, we often assume that we have a densely defined operator. This is helpful because it immediately implies that the Hilbert space adjoint t star exists. And moreover, in the last video we have shown that t star is always a closed operator, which means that the graph of t star is closed, which comes from the fact that the graph is given by an orthogonal complement. However, the downside here is that in general, t star is not densely defined anymore. We can only guarantee that if we assume that our original operator t is a closable one. This is a really nice result because under this assumption we can form the adjoint of t star again. Otherwise it would not be possible because the adjoint only exists if we have a densely defined operator. And with that knowledge we can immediately make a claim for the kernel of the Hilbert space adjoint. So let's simply take t as a densely defined operator and let's look at the kernel of t star. So the only thing we know is that t star is a well-defined closed operator. And the kernel of t star has to be a closed subspace in Y. And there you might already know another subspace in Y, namely the range of t. And indeed, the orthogonal complement of this range is exactly the kernel of t star. And that's already the whole relation we want to prove now. And this is not so complicated because we can just use the defining property of the adjoint, which simply tells us that we have an identity between the two inner products in Y and X. We can look at ytx as the inner product in Y, and this should be equal to an inner product in X, namely t star y with X. So pushing t to the other side is exactly what the Hilbert space adjoint should do. And most importantly, this equality holds for any vectors in the two domains. However, now we are interested in the kernel of t star, so points in the domain that are sent to 0. So vector y lies in the kernel of t star if and only if t star y is equal to 0. However, now if we put this 0 vector into the inner product, we still get out 0. Therefore, the right hand side from above definitely has to vanish. And of course, there it does not matter which arbitrary point x from the domain of t we choose. But there we can also use the fact that dt is a dense subspace in X, which means that the orthogonal complement of dt is just the 0 vector. This means that we also get the other implication here, because if this inner product is equal to 0 for all x in the domain of t, this vector here has to be the 0 vector. Okay, so this is very nice, and now we can use our equality from above to go to the left hand side. Hence we can just write that the inner product ytx is equal to 0 for all x in the domain of t. And exactly there you should see that tx just describes the whole range of the operator t. Hence what we have with this equation here is that y is orthogonal to the range of t. So we just get that y lies in the orthogonal complement of the range of t. And that's already the proof of the whole proposition, because we have shown that the two spaces coincide. So this is important to remember. This equation also holds for unbounded operators. Moreover, what we could also do is to use the orthogonal complement on both sides. then we are still talking about closed subspaces in the Hilbert space Y, which means we just have a double orthogonal complement in a Hilbert space. And there we already know this is the original space if we have a closed subspace. However, in contrast to kernels, a range does not have to be closed in general. Therefore, in general formulas like these, we always have to put the closure on the range of T. Moreover, these two formulas here can easily be combined, and then we see we have a nice decomposition of Y into two orthogonal parts. So maybe let's simply sketch that. Let's assume that this one is our Hilbert space Y. And then we find two closed subspaces in it, namely the kernel of the adjoint, and orthogonal to that, the closure of the range of T. And now both things together just span the whole Hilbert space as a direct sum. So this is what our result here tells us. The Hilbert space Y is split into two parts by the operator T. And since we will use this composition later in this video series, let's formulate it as a corollary. And in fact, we can also get a nice decomposition of our Hilbert space X if we assume that T is a closable operator. Indeed, closable here allows us to use the adjoint of the adjoint. In other words, we can just use the formula from above and apply it to T star instead of T. So this is definitely correct because T star is also a densely defined operator. However, now these two spaces here live in the Hilbert space X instead of the Hilbert space Y. And moreover, we already know that the double adjoint of T is just the closure of T. Therefore, the kernel on the left-hand side is quite simple. We just have the kernel of this closed operator. Hence, if T is already a closed operator, this would be just the kernel of T. And moreover, this whole thing implies that we get a nice decomposition of the Hilbert space X. Namely, we have the closed kernel and the orthogonal complement of it, which is the closure of the range of T star. So there, the adjoint is used for the range. And on the other hand, we already know it's the other way around for Y. So there, as written before, we have the adjoint in the kernel. So there we have two decompositions with a direct sum, and we also already know more because we know they are orthogonal to each other. Therefore, you could also say this denotes an orthogonal sum. So in particular, this might be really helpful for self-adjoint operators, so where T star is equal to T again. And that's exactly what we will talk about in the next video. So I really hope I meet you there again, and have a nice day. Bye bye.